Everything you think you know about our cosmic neighborhood is wrong. Those two faint clouds in the southern sky aren't just galaxies. They are ancient relics carrying a hidden message, and we are running out of time to hear it before our own galaxy swallows them whole. What is the secret they're hiding? In the grand cathedral of the cosmos, we are taught to look for grandeur in the brightest lights. We seek out the sprawling, glittering arms of spiral galaxies and the ancient golden haze of giant ellipticals, assuming that scale is the true measure of significance. We are drawn to the spectacle, to the cosmic fireworks of quasars and the majestic sweep of galactic mergers. But what if the most profound stories, the most transformative secrets are not written in the brightest ink? What if the universe hides its deepest truths, not in plain sight, but in the quiet, humble corners of the night sky? This is the story of the cosmic underdogs, the forgotten siblings of giants like our own Milky Way. They are the dwarf galaxies, faint whispers of starlight that we are only now beginning to understand. For centuries, we saw them as mere satellites, insignificant baubles adorning the cosmic titans. We saw them as simple primitive remnants of a bygone era, the unevolved fossils of the early universe. We were wrong. Within their modest glow lies a history that predates our own, a physics that challenges our most fundamental assumptions, and a potential for life that could redefine our place in the universe. Imagine a library where the most important volumes are not the enormous gilded tomes on display, but the small, dusty chapbooks hidden in the shadows. This is the role of the dwarf galaxies. They are not merely footnotes in the cosmic story. They are the hidden chapters, the secret appendices that contain the keys to the entire narrative. They are the keepers of the universe's oldest light, their stars acting as time capsules from an epoch when the cosmos was young and its rules were still being written. They force us to confront a humbling truth that our obsession with size and brightness may have blinded us to the places where the real mysteries are buried. Their story is not one of insignificance, but of profound, overlooked importance. It is the story of everything we do not yet know, a quiet revolution in our understanding that begins not with a bang, but with a faint, steady glow. For millennia, they were smudges of light known only to those who lived under a southern sky, ghostly clouds, adrift in a deep sea of stars. Indigenous cultures across the southern hemisphere, from the Aboriginal peoples of Australia to the San peoples of southern Africa, wove them into their deepest mythologies. They were the campfires of ancestors, the hunting grounds of celestial spirits, markers of seasonal change, and portals to the dream time. They were a part of the human story long before they had a name in the lexicons of the West. Their formal introduction to Western science came in the early 16th century during a voyage of breathtaking ambition and devastating cost that would forever change our map of the Earth. As the Portuguese explorer Ferdinand Magellan navigated the treacherous icy straits that would one day bear his name, his Venetian chronicler Antonio Pigafetta diligently noted two clouds of mist that seemed to follow their ships through the unfamiliar nights. These celestial companions were, of course, the Large and Small Magellanic Clouds, now named in honor of the captain who would never complete his circumnavigation of the globe. They are our closest and most intimate galactic neighbors. The Large Magellanic Cloud, or LMC, is a sprawling irregular city of some 30 billion stars, lying about 160,000 light-years away. It is a chaotic marvel marked by a prominent bar-like structure and a single misshapen spiral arm, the scar of past gravitational brawls. Its smaller, even more distorted sibling, the Small Magellanic Cloud, or SMC, holds about 3 billion stars and lies slightly farther at 200,000 light-years distant. To the naked eye, They appear as detached luminous pieces of the Milky Way itself, ghostly echoes of our own galactic home. But they are much more than that. They are a dynamic duo, a celestial partnership bound by gravity's invisible tether, forever circling our own galaxy in a slow cosmic dance that is both beautiful and doomed. They are not just neighbors. They are living laboratories offering us a front-row seat to the processes of galactic evolution interaction and eventual consumption. The universe is not a peaceful place. It is a relentless dynamic ecosystem built upon a brutal yet profoundly creative cycle of consumption and assimilation. In this cosmic food web, our own Milky Way is an apex predator, a majestic cannibal that has grown to its current sprawling size by devouring its smaller kin over billions of years. This is not a metaphor. It is a gravitational reality. Within the vast invisible halo that envelops our galaxy, astronomers have found the ghostly remains of this cosmic carnage. They are the stellar streams, the shredded remnants of dozens of dwarf galaxies that strayed too close, their stars and gas stretched into ethereal river-like structures that arc across our sky monuments to feasts of the distant past. This process of galactic cannibalism has not ended. The Magellanic Clouds are the next course on the menu. Pulled by the quiet, incessant patience of our galaxy's gravity, they are spiraling inward on a path that is both graceful and terminal. Their dance is a countdown. In about 2.4 billion years, a collision is destined to occur. The clouds will be torn apart, their stellar structures unraveled by the immense tidal forces of the Milky Way. Their stars will be scattered and flung across our halo, becoming lost and indistinguishable members of our own galaxy. Their vast clouds of gas and dust will be siphoned off, crashing into our galactic disk and fueling a new spectacular generation of star birth. They will be erased from the night sky, their distinct identities, as the celestial companions of humanity, absorbed into the very fabric of their captor. But this is not merely a story of destruction. It is one of transformation. In this cosmic ecosystem, the devoured provide the very nutrients that allow the devourer to grow and evolve. The Magellanic Clouds are not just victims. They are vital contributors, the final enriching meal that will reshape the future of our home galaxy. Their assimilation will trigger a renaissance of creation, a final brilliant burst of activity before the Milky Way itself faces its own colossal merger with the Andromeda Galaxy billions of years further down the cosmic road. Their final act is a testament to the universe's unsentimental yet deeply interconnected nature. In the 1970s, as a new generation of radio telescopes began to listen to the universe in wavelengths invisible to the human eye, astronomers discovered something extraordinary. Trailing behind the Magellanic Clouds and connecting them to our Milky Way was a structure of unimaginable scale. It was not a bridge of stars, but a vast ethereal river of neutral hydrogen gas, a cosmic umbilical cord stretching over 300,000 light-years across the southern sky. They called it the Magellanic Stream. This river of whispers contains enough raw material to forge billions of new stars, a silent gaseous testament to the ongoing gravitational drama between the clouds and our galaxy. For decades, the leading theory for its existence was elegant in its simplicity. The stream was a result of tidal stripping, where the immense gravity of the Milky Way relentlessly tears gas from the smaller galaxies as they orbit, leaving a trail of debris like cosmic breadcrumbs. This model painted a clear picture of the clouds as passive victims, slowly bleeding out as they are pulled toward their inevitable doom. It was a story of pure gravitational mechanics, a clockwork interaction that seemed to explain the stream's existence. Problem solved. But not quite. The universe is rarely so simple. As our observations grew more sophisticated and our computer simulations more powerful, cracks began to appear in this tidy explanation. The simple tidal stripping model couldn't account for the stream's enormous mass, its peculiar shape, or its surprising longevity. It should have dissipated long ago, dissolved by the hot halo of our own galaxy. The story of the Magellanic Stream became more complex, its quiet whispers hinting at forces and histories far more mysterious than gravity alone could explain. The river was not just a trail of debris. It was a clue, a puzzle written in invisible ink across the sky, pointing toward a deeper hidden truth about the lives of these celestial companions. The puzzles surrounding the Magellanic Stream demanded a new idea, a missing piece that could explain its improbable survival. The answer, when it came, was as elegant as it was invisible. In 2020, astronomers using archival data from the Hubble Space Telescope found compelling evidence that the Magellanic Clouds are not naked travelers in the cosmic dark. They are encased in their own protective halo, a massive ionized corona of hot gas. This corona, weighing as much as 10 billion suns, acts as an invisible shield, a buffer that preserves the clouds from complete and rapid disintegration as they plow through the tenuous gas of the Milky Way's own halo. It is this shield that interacts with our galaxy, creating the friction and pressure that help to pull the Magellanic Stream into existence and sustain it. This discovery was a triumph of modern astrophysics, a beautiful solution to a long-standing problem. It showed that the clouds were far more resilient and robust than we had ever given them credit for. They were not simply bleeding out. They were engaged in a complex, high-energy interaction with their massive neighbor. And yet, as is so often the case in science, the solution to one mystery only served to reveal a deeper one. Analysis of the light passing through the Magellanic Stream revealed unusual abundances of certain elements, particularly metals that didn't quite match the known chemical composition of the clouds themselves. The invisible shield explained the stream's survival, but it could not explain its strange contents. Where did these excess elements come from? Could this be the chemical fingerprint of ancient forgotten stellar explosions whose enriched gases were captured by the stream? Or was it something else entirely, the faint elemental residue of processes not born from nature, a chemical anomaly that hints at an artificial origin? The mystery of the stream had deepened. Imagine looking at a familiar friend, someone you've known your entire life, only to discover that they are not one person, but two, their identities perfectly superimposed, one hiding behind the other. In late 2023, the world of astronomy experienced just such a moment of profound revelation. A team of scientists using exquisitely precise data from the European Space Agency's Gaia spacecraft, a mission designed to map the positions and velocities of over 1 billion stars with unprecedented accuracy, turned their gaze to the Small Magellanic Cloud. For centuries, we saw it as a single chaotic entity, a messy afterthought to its larger sibling. But the data told a different, almost unbelievable story. The SMC they announced is not one galaxy, it is two. One component, a distinct collection of stars with its own unique velocity and chemical composition, lies about 16,000 light-years behind the other. Their stellar populations overlap in our line of sight, masquerading as a single distorted object. This discovery of a ghost in the machine, this hidden duality, was a thunderclap in the quiet halls of cosmology. It instantly solved long-standing puzzles about the SMC's strange, elongated shape and its oddly distributed pockets of star formation. But as it answered old questions, it raised a new and even more profound one. How did two distinct dwarf galaxies come to be so perfectly aligned, moving together through space, as if they were one. Was it a cosmic coincidence of unimaginable proportions, a chance alignment frozen in time by our unique viewing angle? Or was it the signature of something far more significant, an ancient merger, a galactic collision captured in a state of suspended animation, its two combatants locked in a gravitational embrace for billions of years? The SMC was no longer just a messy dwarf. It was a crime scene, and the evidence was just beginning to be uncovered. While its smaller sibling harbored secrets of duality, the Large Magellanic Cloud held its own brand of violent mystery. As astronomers charted the intricate dance of its stars, they noticed something peculiar, a population of stars being ejected from its core, flung outwards toward the Milky Way at incredible, almost impossible speeds. These were hypervelocity stars, cosmic runaways moving at millions of miles per hour velocities, so extreme they were fast enough to escape the gravitational clutches of their home galaxy entirely and wander the intergalactic dark. Such speeds demand a powerful engine, a gravitational slingshot of immense and focused force. There are few things in the universe capable of such a feat. A supernova could kick a star, but not with such precision or power. The only truly viable culprit, a black hole. Not just any stellar mass black hole left over from the collapse of a massive star, but something much, much larger. The runaway stars were the first clear evidence, the telltale sign of a hidden monster lurking in the heart of the LMC. For a long time, it was a piece of cosmological common wisdom that dwarf galaxies, with their modest size and shallow gravity wells, lacked the conditions necessary to form and host the supermassive black holes that are found at the centers of giants like the Milky Way and Andromeda. The existence of this unseen beast, betrayed only by the victims it flung into the void, challenged that notion profoundly. It suggested that the lives of dwarf galaxies were far more violent, dynamic, and complex than we had ever imagined. They were not just quiet, cosmic suburbs. They were active, sometimes brutal arenas where the most extreme forces in the universe were at play. The monster in the dark was a sign that our neat categories for the cosmos were about to be torn apart. The evidence was mounting. The runaway stars were the footprints, and they led astronomers directly to the lair of the beast. In 2025, a new generation of observations leveraging the combined power of telescopes across the globe finally confirmed their suspicions. Lurking in the center of the Large Magellanic Cloud was not just an intermediate mass black hole, but a true monster of the cosmos, weighing in at an estimated 100,000 times the mass of our Sun. This was a bombshell that sent shockwaves through the astronomical community. According to our established understanding of galactic evolution, a relationship known as the M-sigma relation, the mass of a central black hole should be proportional to the mass of its host galaxy's central bulge of stars. The LMC's black hole shattered this rule. It was grotesquely oversized, a giant's heart in a dwarf's body. This discovery forced a profound rewriting of our models. How could such a relatively small and unstructured galaxy harbor such a massive singularity? The implications were staggering. One possibility is that the seeds of supermassive black holes form much earlier and more easily in the universe than we previously thought, and that the LMC is a pristine example of this early process. But a more dramatic and tantalizing explanation has gained traction. The LMC was not its original owner. It must have stolen or inherited this black hole from a past merger with another smaller galaxy, consuming its victim's heart and making it its own. This act of galactic piracy would have fundamentally altered the LMC's evolution, providing it with a powerful central engine that could drive star formation and shape its destiny. The hidden monster was not just an engine of destruction. It was a relic, a trophy, from a forgotten cosmic conquest and a testament to a far more violent and predatory history than we ever imagined for these faint clouds of light. But what if this black hole, this stolen heart, is not a natural relic at all? Here we must take a step from the shores of established science into the deep, speculative ocean of what might be possible. In the grand theater of the cosmos, could a singularity of this nature be something more? An advanced Kardashev Type 2 or 3 civilization, with a mastery of physics that borders on the magical from our perspective, might view a black hole not as a cosmic hazard, but as the ultimate tool. It is a near-infinite source of energy that can be tapped through the Penrose process. It is a perfect computational device, a gravitational computer of unimaginable power. And most tantalizingly, it is an eternal information storage unit. Could the LMC's oversized black hole be a piece of dormant technology, a harnessed singularity once used to power an entire galactic civilization, now silent and waiting? The laws of quantum mechanics, as first theorized by the great Stephen Hawking, suggest that black holes are not entirely black. They do not just consume, they also leak. Through a process known as Hawking radiation, they slowly evaporate over unimaginable timescales, returning their energy to the universe. And crucially, this radiation is not random. It is thought to carry information scrambled and faint about everything that has ever fallen in. Theoretical physicists have posited that it might be possible to encode vast amounts of data onto the two-dimensional surface of a black hole's event horizon, preserving it for eternity. Could the faint quantum whispers emanating from this heart of darkness be more than random static? Could they be fragments of a lost library, the faint, ghostly echo of a forgotten civilization's collective memory, broadcast across the ages for anyone with the means to listen? We now turn to an even greater and more pervasive mystery, an invisible architecture that shapes the very cosmos we see. It is dark matter, the elusive, unseen substance that, according to our best measurements, makes up a staggering 85% of all the mass in the universe. It does not emit, absorb, or reflect light, rendering it utterly invisible to our telescopes. We know it is there only through its quiet, persistent gravitational influence on the things we can see. It is the gravitational scaffold upon which galaxies are built, the invisible loom that weaves the vast cosmic web of filaments and voids. And dwarf galaxies like the Magellanic Clouds are the perfect laboratories for studying it, because they are relatively simple systems with a high ratio of mass to light their internal motions, and their orbits around the Milky Way are overwhelmingly dominated by the gravity of their dark matter halos. By meticulously mapping the orbits of their stars and gas clouds, we can in essence map the shape of the invisible. Recent maps from projects like the Dark Energy Survey have revealed these halos in stunning detail, showing vast asymmetric clouds of dark matter enveloping the clouds, their shapes distorted and stretched by the relentless gravitational tug-of-war with the Milky Way. These maps are more than just pictures of nothingness. They are blueprints of the hidden forces that govern the lives and deaths of galaxies. And within their strange, lopsided shapes lie clues that challenge our most fundamental theories of cosmology, hinting that the nature of this invisible substance is far stranger than we ever predicted. The loom of dark matter weaves a complex and baffling tapestry, and the dwarf galaxies are where we can finally begin to see its threads. As our maps of these invisible dark matter halos became more and more precise, a stubborn and deeply troubling paradox emerged. It was a crack in the very foundations of our standard cosmological model, the elegant theory known as lambda cold dark matter, or lambda CDM. This theory has been stunningly successful at explaining the large-scale structure of the universe, but it makes a very specific prediction about the inner workings of dark matter halos. It predicts that they should be cuspy, that their density should rise sharply and steeply to a peak at the very center of a galaxy. Yet, when we observe the real universe, especially in dwarf galaxies, where the effects of dark matter are so clean and pronounced, we find something different. Their halos are often cored, with a flatter, less dense center, as if something has scooped out the middle. This glaring discrepancy is known as the core-cusp problem, and it has vexed cosmologists for years. It is one of the most significant challenges to our understanding of the universe's fundamental composition. One possible explanation is that dark matter is more complex than we thought. Perhaps its particles don't just pass through each other like ghosts, as the cold dark matter model assumes. Perhaps they can interact with each other, creating a kind of pressure that smooths out the central cusp over cosmic time. This idea of self-interacting dark matter would represent a revolution in our understanding, opening up a whole new sector of particle physics. But it is not the only possibility. What if the cores are not flat because of a new kind of physics, but because of a very old kind of engineering? What if the missing mass wasn't pushed aside, but taken? Let us allow ourselves a flight of fancy, guided by the strange clues the universe has so generously provided. If a truly advanced civilization could master the fundamental forces of nature, what might it do with a substance as abundant and gravitationally potent as dark matter? Perhaps it wouldn't just observe it, it would manipulate it. It could engineer this invisible substance to create structures of unimaginable scale and utility. In this light, the flattened cores of dwarf galaxies are not a paradox, but a technosignature. They could be the sign of dark matter mining, where the densest central regions are harvested for energy, or perhaps for the creation of the exotic matter needed for warp drives and stable wormholes. Some theorists have even speculated that advanced intelligences could weave dark matter into dark highways, stable gravitational corridors between star systems, or even galaxies, allowing for a form of faster-than-light travel along hidden invisible pathways. This leads to an even more tantalizing idea, one born from another persistent cosmic puzzle known as the satellite problem. The fact that we observe far fewer dwarf galaxies orbiting the Milky Way than our simulations predict there should be. What if the missing satellites are not gone, but merely hidden? What if they are dark dwarfs, artificial constructs built entirely from dark matter, shadow realms designed as stealth colonies to evade detection from less advanced and potentially hostile civilizations? In this grand speculative vision, the Magellanic Clouds with their extended manipulated dark matter halos might be the gateways to this hidden network, the only visible outposts of a vast unseen galactic empire. The clues, it seems, point not just to new physics, but to a cosmos far more populated and far more engineered than we ever dared to dream. As we dive deeper into the stellar populations of the Magellanic Clouds, another profound and unsettling enigma reveals itself. This mystery is written not in what is there, but in what is conspicuously missing. When astronomers carefully catalog the ages of the globular clusters, the dense, ancient spherical swarms of stars that orbit the clouds, like bees around a hive, they find a startling and inexplicable gap. There are plenty of very old clusters, ancient relics dating back more than 12 billion years to the dawn of galaxy formation. And there is a healthy population of young, brilliant blue clusters, less than 1 billion years old, born from recent bursts of star formation. But there is a glaring void in between. Both the LMC and the SMC are almost entirely devoid of star clusters aged between roughly 1.5 and 4 billion years. For a period of 2.5 billion years, an immense span of time, something appears to have shut down the formation of these massive stellar nurseries. Natural explanations have been proposed, of course. Perhaps a particularly violent close encounter with the Milky Way tidally stripped the clouds of the gas needed to form new clusters. Or perhaps their orbits carried them through a particularly empty region of space, starving them of the raw materials for creation. But the sheer precision of this gap, this clean slice taken directly out of their stellar history, feels too neat, too orchestrated to be a mere accident of gravitational dynamics. It feels less like a slow starvation and more like a sudden, externally imposed event. It is a void in time, a missing chapter in the galactic history books that hints at a dramatic and perhaps even catastrophic past. A 2.5 billion year gap in the life of a galaxy is an immense span of time, an epoch of profound quiet where there should have been the roar of creation. What could cause such a prolonged and complete hiatus? The data leaves us with deeply unsettling possibilities. Perhaps this age gap truly does mark a period of cosmic catastrophe, a galactic-scale disaster that sterilized the clouds and halted all major star formation for eons. A nearby hypernova, the most powerful type of stellar explosion, could have bathed the galaxies in lethal radiation. Or perhaps the newly discovered black hole at the LMC's heart went through a particularly violent quasar phase, its jets of energy blasting away the gas needed for new stars to form. But another more sinister theory takes shape in the speculative corners of cosmology. What if this void represents a great silence, imposed not by nature, but by intelligence? It could be the deep and lasting scar of a long-forgotten war between nascent civilizations in the LMC and SMC, a conflict so devastating that it resulted in a technological embargo, a mutually enforced moratorium on star formation to conserve precious resources or to hide from an even greater external threat. It might even be the sign of a quarantine, a period when the clouds were deliberately isolated by a galactic overseer to contain a biological plague, or perhaps a runaway, self-replicating artificial intelligence. The void in time might not be an absence of history, but the tombstone of one. It is a chilling reminder that on cosmic timescales, entire empires can rise, fall, and be erased so completely that the only evidence of their existence is a period of unsettling silence. Our journey now pivots from the grand physics of the cosmos to its most profound and intimate potential, the emergence of life. As we peel back the layers of the Magellanic Clouds, we are forced to ask a question once confined to the realm of science fiction: could these faint, humble galaxies be cradles for life? At first glance, they seem like unlikely candidates. The stars within them are, on average, metal poor. In astronomical terms, a metal is any element heavier than hydrogen and helium. This means the clouds contain fewer of the heavy elements, the carbon, oxygen, nitrogen, and iron, that were forged in the hearts of earlier stellar generations, and are the fundamental building blocks of life as we know it. This scarcity of raw materials would seem to be a major obstacle to biology. And yet this very scarcity might be the key to fostering unique and resilient evolutionary paths. Life in a low metallicity environment would by necessity have to be incredibly efficient, adapting to sparse resources in ways we can barely imagine. It might rely on exotic chemistries that we have yet to discover, perhaps using silicon as a backbone instead of carbon, or harnessing energy from sources that are unavailable in our own chemically rich corner of the Milky Way. The clouds are not simply a diluted version of our galaxy. They are a different kind of chemical laboratory, one that has been running a different set of experiments for billions of years. Within them, The recipe for life could have entirely different ingredients leading to forms of biology so alien they would challenge our very definition of what it means to be alive. The search for life in the Magellanic Clouds is not just a search for our counterparts, it is a search for entirely new possibilities. In the heart of the Large Magellanic Cloud lies a cosmic crucible, one of the most violent and ferociously active star-forming regions in our entire local group of galaxies. It is the Tarantula Nebula, a sprawling chaotic web of glowing gas, colossal young stars, and the shredded remnants of recent supernovae. It is a place of both creation and destruction, on a staggering scale so bright that it is easily visible to the naked eye as a fuzzy patch of light from the southern hemisphere. If this nebula were as close to us as the Orion Nebula in our own galaxy, it would cast shadows on the surface of the Earth, and its light would be bright enough to read by at night. In 2024, observations from the James Webb Space Telescope pierced its dusty veil, revealing its inner sanctum in breathtaking detail. The images showed intricate glowing filaments of molecular clouds laced with the unmistakable spectral signatures of polycyclic aromatic hydrocarbons, or PAHs. These complex organic molecules' rings of carbon and hydrogen are considered by astrobiologists to be among the fundamental building blocks of life, the precursors to amino acids and nucleotides. Bathed in the intense, sterilizing ultraviolet radiation of the nebula's brilliant young stars, these powers could polymerize into ever more complex structures, a tantalizing hint of prebiotic chemistry taking place on a galactic scale. But what if this magnificent nebula is more than just a natural factory? In the more speculative theories of astrobiology, a place like this would be the perfect target for directed panspermia. It could be a seeded zone, a galactic garden, where an ancient, intelligent civilization deliberately dispersed life-bearing compounds using the nebula's violent churning turbulence as a natural and efficient mechanism to spread the seeds of biology across thousands of light years. It is a wild thought, but in a place as extreme and fertile as the tarantula's web, we cannot rule out the possibility that the seeds of life were not just born there, but planted. The Small Magellanic Cloud, with its lower mass and chaotic dual galaxy structure, offers its own unique brand of astrobiological intrigue. Its star fields are dominated by brilliant young hot blue stars, seemingly hostile to life as we know it, bathing their surroundings in sterilizing radiation. But hidden within its misty expanse are quieter pockets, cooler dust-shrouded regions, where habitable zones could exist around long-lived stable stars. In 2025, the European Space Agency's Plato mission, a space telescope specifically designed to hunt for Earth-like planets in the habitable zones of Sun-like stars, turned its sensitive gaze toward the SMC. The initial data, though preliminary, revealed a handful of promising candidates, rocky terrestrial worlds orbiting quiescent red dwarf stars, where the conditions might be just right for liquid water to exist on their surfaces, despite the galaxy's metal-poor environment. These worlds, if confirmed by follow-up observations, would be extraordinary laboratories for life. They could host extremophiles capable of thriving in high radiation conditions, developing biological defenses far beyond anything seen on Earth. Or perhaps they could even host life based not on carbon, but on silicon, an element with similar chemical properties that is far more abundant in their planetary crusts. The recently discovered double galaxy nature of the SMC amplifies this potential exponentially. The foreground component, with its separate stellar history and distinct chemical makeup, might have preserved isolated biospheres untouched by the influences of the Milky Way or its twin for billions of years. They could be true islands of independent evolution places where the experiment of life has been run twice under slightly different conditions, in the very same patch of sky. The SMC is not just one potential cradle for life. It is two. Where is everybody? This was the simple yet monumentally profound question posed by the physicist Enrico Fermi during a casual lunch conversation in 1950. It has haunted us ever since. If the universe is as vast and as old as we know it to be, and if the ingredients for life are as common as we believe them to be, then the cosmos should be teeming with intelligent technological civilizations. Yet when we look to the stars, we are met with a deafening cosmic silence. This is the Fermi paradox, and it is one of the deepest and most troubling mysteries of our time. But perhaps the answer lies not in a lack of life, but in a fundamental misunderstanding of how advanced life behaves. Perhaps the silence is not an absence, but a choice. Perhaps advanced civilizations do not announce themselves with bright lights and loud radio broadcasts that shout their existence to a potentially dangerous cosmos. Perhaps they hide. And dwarf galaxies like the Magellanic Clouds are the perfect hiding place. Unlike the crowded, violent, and chaotic metropolis of a large spiral galaxy like the Milky Way, where nearby supernova gamma-ray bursts and the gravitational turmoil near the galactic center can sterilize vast regions of space dwarfs, offer a quiet, stable cosmic suburbia. Their relative isolation and slower pace of evolution could allow life to arise and develop undisturbed for billions of years, perhaps leading to ancient, wise, and deeply conservative civilizations that value subtlety and stealth over noisy expansion. They would have witnessed the rise and fall of countless younger, more reckless species in the brighter galaxies, and learned the ultimate lesson of cosmic survival: to be powerful is to be quiet. The Fermi paradox might be answered here. The aliens are not missing. They are cloistered, their faint signals deliberately cloaked their empires, built in the shadows, lost in the overwhelming noise of the cosmos. In recent years, radio astronomers have detected a new and profoundly baffling cosmic phenomenon: fast radio bursts, or FRBs. These are millisecond-long, intensely powerful blasts of radio waves originating from distant galaxies that can unleash as much energy in a fraction of a second as our sun does in an entire day. While natural explanations, such as violent eruptions from highly magnetized neutron stars called magnetars, are the leading candidates, some FRBs defy easy categorization. A handful of bursts detected from the direction of the Magellanic Clouds have exhibited patterns that are simply too regular, too structured, to be dismissed as mere noise. They repeat at predictable intervals. Their frequencies contain hints of complex layered modulation, and their polarization, the orientation of the light waves, suggests an origin that is coherent and artificial. Could these be more than just natural cataclysms? Could they be the very whispers we've been straining to hear across the cosmic ocean? In the grand scheme of possibilities, they could be anything. Perhaps they are the automated beacons of long-extinct societies, cosmic lighthouses still guiding travelers through the intergalactic void, their creators long since turned to dust. Or perhaps they are something more immediate, something more vital, deliberate targeted messages from intelligences that are still very much alive, a greeting, a warning, or an invitation sent whispering across the void from our closest galactic neighbors. The silence may not be empty, after all. We may have simply been listening on the wrong frequency. The story of the Magellanic Clouds is not written only in the cold light of distant stars and the austere language of physics. It is also written in the vibrant, enduring myths of humanity. For tens of thousands of years before they were named for a European explorer, indigenous cultures in Australia, South America, and Africa gazed up at these celestial smudges, weaving them into the very fabric of their cosmologies. They were not just objects to be observed, they were actors in a living celestial drama. In some Aboriginal Australian traditions, the LMC is seen as the campfire of an ancestral spirit named Ngurunderi, while the SMC is the camp of his wives. For the Tupi people of Brazil, they were seen as celestial fountains, the source of all the waters on Earth. These are not just fanciful tales. The emerging field of archaeoastronomy, which studies how ancient peoples understood and interacted with the heavens, has revealed that these myths often encode sophisticated and surprisingly accurate astronomical knowledge. Oral traditions passed down for millennia describe falling stars and great battles in the sky that align eerily with our modern understanding of meteor showers that appear to originate from the direction of the clouds and the violent gravitational interactions that shape the Magellanic Stream. Could these myths be more than just metaphors for the natural world? Could they be the faint cultural echoes of ancient, long-forgotten visitations, where explorers from the clouds once interacted with early humanity, leaving their mark not in stone artifacts, but in our oldest and most sacred stories? It is a profound thought that the first contact may have already happened, and the only record of it lies dormant in the bedrock of human myth. Among the most skilled and courageous celestial navigators in human history were the Polynesian voyagers who settled the vast, lonely expanse of the Pacific Ocean in their magnificent outrigger canoes. For them, the sky was not just a beautiful backdrop. It was a map, a compass, a clock, and a calendar. They carried no magnetic instruments, only a deep, multi-generational knowledge of the stars. And they used the Magellanic Clouds as crucial wayfinders, fixed points in the heavens that could guide them across thousands of miles of open ocean. In the traditions of the Maori people of New Zealand, the Large Magellanic Cloud is sometimes known as Te Waka o Tamarereti, the canoe of the spirit Tamarereti. This ancient poetic vision of the clouds as celestial vehicles, as vessels for travel, resonates with a startling and profound depth when we consider their potential role in a mature galactic ecosystem. Just as Polynesian sailors used islands as stepping stones to cross the vast ocean, future interstellar explorers, or perhaps those who came long before us might use dwarf galaxies as strategic waystations to cross the even vaster void between galaxies. They offer a sanctuary from the radiation and gravitational hazards of the crowded galactic core. They are a repository of raw materials, hydrogen gas for fuel, asteroids for minerals, and they provide a stable, quiet platform for long-range communication relays. The ancient myth of the sky canoe might be more than just a story. It could be a profound premonition, a deep cultural echo of a truth we are only now beginning to grasp with our science. It is a hint that the ultimate purpose of these dwarf galaxies is to serve as vessels carrying not just the spirits of myth, but entire civilizations toward an unknown cosmic shore. As our perspective on the universe matures, a new and tantalizingly provocative field of science is beginning to emerge: space archaeology. It is a discipline born from a simple yet profound realization. It treats the cosmos not as a pristine, untouchable wilderness, but as a potential historical site, a vast, untapped landscape that may be littered with the relics of ancient intelligences. If civilizations like stars are born live and die over billions of years, then surely they must leave something behind. And dwarf galaxies, with their quiet, stable environments, their slower rates of stellar evolution, and their immense longevity, are the perfect cosmic vaults for preserving such artifacts. This is not a search for flying saucers or little green men. It is a rigorous, data-driven search for technosignatures, the subtle, persistent, and quantifiable evidence of technology. This cosmic dig seeks out anomalies that defy any and all natural explanation, unusual thermal signatures, from stars that suggest massive artificial structures, coherent radio, or laser signals that carry the unmistakable imprint of mathematics. Non-random patterns in the light of distant stars, or even the chemical fingerprints of industrial pollution in the atmospheres of exoplanets. It is the most ambitious archaeological project ever conceived, and the Magellanic Clouds, our closest and most accessible dwarf galaxies, are the prime targets for this extraordinary search. They are the nearest, most promising ruins, a place where we might unearth the silent remnants of an empire older than humanity itself. The dig has already begun. One of the most audacious and exciting concepts in the field of space archaeology is the search for megastructures. These are hypothetical feats of astroengineering built by civilizations so advanced they can manipulate matter on a planetary, stellar, or even galactic scale. The most famous of these is the Dyson sphere, or more plausibly, a Dyson swarm, a vast constellation of solar collectors orbiting a star designed to capture nearly all of its energy output to power an interstellar society. Such a structure would be invisible in optical light, but it would betray itself by glowing brightly in infrared, radiating away the waste heat from its unimaginable industry. In mid-2025, data from the James Webb Space Telescope pointed at the very heart of the LMC's violent Tarantula. Nebula revealed several massive brilliant stars with anomalous and inexplicable infrared emissions. These hot spots did not align with the known thermal signatures of any natural phenomena, like dusty protoplanetary disks or stellar nebulae. Instead, they mimicked with an eerie precision the predicted spectral signature of the waste heat from a partial Dyson swarm. While skeptics were quick to argue for novel yet unexplained natural causes, the emissions showed a subtle but distinct geometric regularity in their distribution, forming faint hexagonal patterns that hinted at a deliberate artificial design. If these detections are confirmed, if they are real, then they are the first tangible evidence of a civilization that colonized the Large Magellanic Cloud billions of years ago. A silent hidden empire, now betrayed only by the faint residual warmth of its cold, silent, and unimaginably ancient machines. While some archaeologists of the cosmos search for the faint heat of forgotten industry, others listen patiently for the whisper of communication. In 2024, radio astronomers using a new, highly sensitive array in the Australian outback detected a series of unusual narrow-band signals emanating from the foreground layer of the Small Magellanic Cloud. Their frequency was far too coherent, too pure to be a natural phenomenon like a pulsar or a quasar. More intriguing still, the bursts repeated at a precise interval of 14 to 20 seconds. This number is not random. The neutral hydrogen line, the frequency at which the most abundant element in the universe, hydrogen, naturally emits radio waves, is 1420 megahertz. It is a universal constant, a cosmic signpost that many SETI researchers have long believed would be used as a marker for any intentional galactic broadcast, a galactic waterhole where all carbon-based life might come to talk. The signal was faint, but it was structured. It carried modulated data packets that resembled advanced mathematically derived error-correcting codes. When a team of cryptographers and linguists managed to decode small snippets, they found what appeared to be binary representations of fundamental mathematical and physical constants, like pi, the golden ratio, and the fine structure constant, extended to thousands of digits with a precision far beyond what could occur by chance. This is the classic textbook hallmark of an intentional transmission, a hello from an intelligence that understands the universal language of mathematics. But what is its intent? Is it a greeting? A hand extended in friendship from a civilization that is still alive? Or is it an epitaph, a final message in a bottle from a society long since turned to dust, a monument to their existence, still broadcasting on a cosmic loop we do not yet know? The search for extraterrestrial intelligence is not confined to the vast crackling silence of the radio spectrum. A parallel effort known as Optical SETI scans the skies for a different kind of signal, brief, powerful, and coherent flashes of laser light. In principle, a focused laser beam is a far more efficient way to send vast amounts of information across the immense distances between stars. In 2025, a team of researchers painstakingly reanalyzing terabytes of archival data from a survey telescope in the Chilean Andes found exactly what they had been looking for. From the direction of the Small Magellanic Cloud, they found a series of faint but statistically significant pulsed flashes at a very specific optical wavelength. The flashes were incredibly brief, lasting only nanoseconds, but they were powerful enough to be distinguished from the random noise of the background stars. And they were structured. The precise timing of the pulses carried what appeared to be gigabits of compressed data. This was not a simple repeating beacon designed to attract attention. It was a targeted data stream, a focused burst of information. But what was its purpose? Were these the last desperate distress calls from a dying civilization, a final plea for help sent out into the infinite void? Or were they something more mundane and perhaps even more exciting? The automated data packets from a reconnaissance probe diligently reporting its findings back to a hidden and still active home base. We may never know for sure, but the faint glint of structured light in the deep darkness proves with a chilling certainty that someone or something is out there. The next great leap in the cosmic dig will come with the launch of the next generation of truly colossal space telescopes, such as the proposed LUVOIR Observatory, a project currently envisioned for the 2040s. With an immense segmented mirror perhaps 15 meters across, LUVOIR will have the power to do something once thought utterly impossible: to directly image Earth-sized exoplanets orbiting stars in the Magellanic Clouds, and to analyze the chemical composition of their atmospheres in detail. This opens up an entirely new and revolutionary avenue in the search for technosignatures. We will finally be able to look for the chemical fingerprints of industry on a planetary scale. An advanced global civilization would inevitably and profoundly alter its planet's atmosphere, leaving behind telltale signs that could be detected across the vastness of intergalactic space. We could look for high concentrations of artificial industrial pollutants, such as chlorofluorocarbons, molecules so complex they are almost impossible to create naturally. We could search for an unnatural and unstable balance of gases, like high levels of both oxygen and methane, a combination that on Earth is a direct and unambiguous signature of widespread biological and industrial activity. With its incredible sensitivity, LUVOIR might even be able to detect the faint reflected glint of artificial cityscapes on the night side of these distant worlds. With this new tool, the search will no longer be for abstract radio signals or faint flashes of light, but for the tangible chemical and physical evidence of a world transformed for better or for worse by the hand of intelligent life. But not all technosignatures are glorious monuments to success. Some may be the quiet, mournful scars of failure, the ghostly remnants of ambitious projects that ended in unimaginable catastrophe. In February 2025, ESA's XMM Newton Space Telescope, an orbiting observatory that sees the universe in the violent light of high-energy X-rays, discovered two peculiar and isolated supernova remnants in the lonely outskirts of the Large Magellanic Cloud. What made them so strange was their location. They were cosmic orphans adrift in the galactic hinterlands, far from any known stellar nursery, with no clusters of young massive stars nearby, that could have produced such titanic explosions. While it's possible they were the remnants of ancient massive stars from a now dispersed and forgotten cluster, a more speculative and chilling theory suggests they could be the scars of failed stellar engineering. Perhaps an advanced civilization, in a desperate search for new energy sources, was attempting to create artificial stars or to harness the power of controlled supernova for propulsion or weaponry. These two isolated expanding shells of superheated gas might be the silent, ghostly evidence of experiments gone horribly and catastrophically wrong. They are a potential warning written in X-rays across the void against the hubris of a civilization that may have reached too far, a somber reminder that the power to create stars is also the power to extinguish civilizations. They are the scars of an ambition that may have burned too brightly. For all our remote searching, for all our patient listening, and our clever analysis of ancient light, there is ultimately only one way to know for sure. We have to go there. The Magellanic Clouds, while dauntingly distant, are not beyond our eventual reach. NASA's proposed Magellanic mission, slated for launch in the mid-2030s, aims to send a fleet of advanced artificially intelligent CubeSats on a multi-decade journey to the Large Magellanic Cloud. Equipped with a new generation of miniaturized sensors and AI-driven analysis tools, they will study the cloud's exoplanetary systems and scan for biosignatures and technosignatures up close in real time. At the same time, ambitious private initiatives like Breakthrough Starshot are refining their audacious plans to send swarms of nanocraft, tiny chip-sized light sail-propelled probes toward the nearest and most promising candidate worlds in the LMC. Propelled by immensely powerful Earth-based lasers, these probes could be accelerated to a significant fraction of the speed of light, potentially arriving at their destination within a single human lifetime. They would send back the first direct close-up images of these alien star systems, forever changing our relationship with the cosmos. These missions, though still on the drawing board, represent humanity's first concrete, tangible steps to follow the whispers and clues we have detected from afar. They are a profound declaration that we are no longer content to just listen from the sidelines. We are ready to join the conversation. We are ready to knock on the door, to truly understand the ultimate destiny of the Magellanic Clouds, and perhaps our own. We must zoom out and place them within the grand architecture of the galactic ecosystem. The universe is not a static collection of isolated objects, but a living, breathing, and constantly interacting system. The Milky Way, the great Andromeda Galaxy, and their dozens of smaller satellite galaxies are all bound together in a complex and intricate web of gravity gas and dark matter. In this ecosystem, everything is connected. In April of 2025, astronomers using the powerful Subaru telescope in Hawaii revealed that the Small Magellanic Cloud is being torn apart not just by the tidal forces of our own galaxy, but by the competing gravitational pull of the Large Magellanic Cloud as well. This cosmic tug-of-war stretches the SMC into its characteristic elongated shape and is responsible for bifurcating the Magellanic Stream, siphoning its precious gas in multiple directions at once. This complex and violent process is more than just destruction. It is nutrient cycling on a cosmic scale. As the smaller galaxies are torn apart, they break down, providing the raw materials, the gas, the dust, and even entire star clusters that fuel the ongoing evolution of the entire local group. It is a perfect, if brutal, example of how the small are sacrificed to sustain the great, a fundamental law of the cosmic food web that plays out over billions of years. The clouds are not just passengers on a journey to oblivion. They are active participants in the life cycle of our galactic neighborhood. In June of 2025, The new European Southern Observatory's Extremely Large Telescope, or ELT, perched high in the thin, dry air of the Atacama Desert in Chile, captured its breathtaking first light images. One of its initial targets was the turbulent core of the Large Magellanic Cloud. The level of detail was revolutionary. For the first time, it could resolve individual stars within the galaxy's densest and most ancient globular clusters. And in doing so, it revealed something utterly astonishing. Stellar highways, coherent river-like streams of young blue stars, all moving in the same direction, migrating out of the cloud and along invisible gravitational gradients towards the Milky Way. The LMC was acting as a cosmic conveyor belt, manufacturing fully formed stellar systems in its core, and then delivering them intact to be seamlessly integrated into the outer disk of our own galaxy. This celestial supply chain, operating over billions of years, could finally explain some of the long-standing and perplexing puzzles about the Milky Way's warped and disturbed outer structure. But seen in a more speculative light, it mirrors a deliberately engineered system with an almost industrial efficiency. Could an ancient and profoundly advanced intelligence have established these gravitational pathways, using them to methodically transport habitats, automated probes, or even entire populations from the quieter suburbs of the LMC to the galactic metropolis? If so, their subtle technosignatures may now be hidden within the chemical makeup of these migrating stars, waiting patiently to be discovered, not hundreds of thousands of light-years away, but right here in our own backyard. The ongoing fragmentation of the Small Magellanic Cloud that ghost in the machine offers one of the most profound and deeply personal possibilities for our own origins. An August 2025 study combining data from multiple telescopes detailed the discovery of what they termed ejected clumps, dense, gravitationally bound pockets of gas and dust being flung out of the chaotic SMC and hurtling on a trajectory that will eventually intersect with the outer halo of the Milky Way. Subsequent radio observations from the ALMA telescope in Chile showed that these clumps are incredibly rich in the very same complex organic molecules found in the LMC's Tarantula Nebula. This raises the tantalizing possibility of a natural, or perhaps even an engineered form of panspermia, where life itself is transported between galaxies. These clumps, acting as cosmic incubators, could seed the comets in our own distant Oort cloud, which then, over millions of years, would migrate inward and deliver their precious organic cargo to nascent rocky planets like the early Earth. If this is true, then our planet's biosphere, our entire evolutionary history, may have its most ancient roots not here in the soil of our own world, but in the stellar nurseries of the Small Magellanic Cloud. Our very DNA could be a hybrid of terrestrial evolution and extraterrestrial imports, a biological message sent across the void billions of years ago. Taking it a step further, one could imagine an advanced society deliberately bioengineering these clumps, encoding entire genetic libraries, or even hardy nanobots within them, a galactic seed vault strategy designed to ensure the survival and propagation of life against any and all cosmic catastrophes. We may not just be looking at our neighbors, we may be looking at our creators. In a widely discussed 2025 TED Talk that electrified the scientific community, the brilliant and iconoclastic astrobiologist Dr. Sarah Walker proposed a radical new way of looking at the Magellanic Clouds and their ever-growing list of anomalies. She argued that we should see them not as passive objects of study, but as active participants in a galactic dialogue. Perhaps, she posited, they are not just hiding secrets, but actively teaching lessons. She argued that the clouds could function as cosmic mentors, their unusual physics and unresolved mysteries serving as a natural pre-packaged curriculum for emerging technological civilizations like our own. By studying their incredible resilience in the face of cosmic isolation and gravitational harassment, we learn vital lessons about how to survive in the void. By deciphering their complex and violent gravitational interactions, we learn the fundamental principles of stellar and galactic engineering. And by confronting their deepest paradoxes, like the 2.5 billion-year age gap and the stubborn core-cusp problem, we are pushed by necessity to develop a deeper, more nuanced, and more humble understanding of the universe and our place within it. In this elegant and hopeful view, the Fermi paradox is resolved not by hiding, but by teaching. Advanced civilizations endure not through noisy conquest and expansion, but through quiet, patient symbiosis, using stable, long-lived dwarf galaxies as neutral grounds, as cosmic universities for the education and cultivation of their younger, more volatile galactic neighbors. The silence is not an absence. It is a classroom. For too long, the culture of modern science has dismissively treated ancient myths and indigenous knowledge as mere superstition, as the fanciful and primitive attempts of our ancestors to explain a world they could not comprehend. But a new, more holistic and more humble approach is beginning to emerge, one that seeks to find the powerful intersection between our most advanced scientific knowledge and our most ancient human wisdom. In June of 2025, a groundbreaking symposium in Sydney, Australia, brought together leading astrophysicists, cultural anthropologists, and Aboriginal Australian elders to discuss the Magellanic Clouds. The elders spoke of the dream time, a timeless foundational realm that exists parallel to our own, a concept that defies easy translation into Western thought. They described the clouds not as distant objects, but as portals, as gateways to this other, deeper reality. The physicists, in turn, spoke in their own language of mathematics and observation. They spoke of the bizarre paradoxes of quantum mechanics, of the non-local interconnectedness of spooky action at a distance, and of the speculative but mathematically plausible theories of the multiverse, where other universes with other laws might brush up against our own. The language was different, the methodologies were worlds apart, but the core concepts were hauntingly and profoundly similar. These collaborations suggest that indigenous lore may not just be encoding simple naked-eye observations of the night sky, but a deeper, more intuitive, and perhaps even more accurate understanding of the nature of reality, a holistic perspective that our purely empirical reductionist science may have lost along the way. To truly understand the secrets of the Magellanic Clouds, it may not be enough to simply listen to the data from our telescopes. We may also have to learn to listen to the stories of our oldest ancestors. As we stand on the precipice of unraveling these profound secrets, we as a species face a monumental choice, a defining question of our maturity. The potential technologies and knowledge hidden within the Magellanic Clouds, unlimited energy from harnessed black holes, faster than light travel via engineered dark matter highways. The biological secrets of panspermia could represent humanity's greatest inheritance. They could be the key to solving our most intractable terrestrial problems and propelling us into a true galactic future. But they could also be a terrible and cautionary tale, the 2.5 billion-year Great Silence. The stray supernova, remnants that look like industrial accidents, the faint whispers of ancient forgotten wars. These all speak to the immense and terrifying dangers of unchecked technological ambition. What if awakening these dormant forces triggers a backlash we cannot comprehend? What if we stumble upon a quarantine zone and in our ignorance unleash a threat we cannot possibly control? The ethical debates are already beginning to rage in scientific and philosophical circles. Do we have the right to exploit these potential secrets for our own gain, treating the clouds as a cosmic resource to be plundered? Or should they be preserved as a universal heritage, a cosmic monument to be studied with reverence and caution, but never disturbed? How we choose to approach the Magellanic Clouds will define our character as a species. Will we be conquerors, or will we be custodians? Will we choose inheritance, or will we heed the warning? In the final analysis, the Magellanic Clouds are more than just galaxies. They are mirrors. In their faint, mysterious, and troubled light, we see a reflection of our own potential, our deepest hopes, and our most profound fears. They are living repositories of a past that may stretch back to the very dawn of the universe, and they are the silent architects of a future that will long outlive us. They challenge our science at every turn, they enrich our most ancient myths, and they force us with their persistent and unsettling anomalies to confront the biggest questions of our existence. Are we alone? What is our purpose? What is our ultimate destiny in the stars? As we stand here today at this particular moment in cosmic history, our telescopes piercing ever deeper into their misty shores and our minds expanding to encompass their profound and dizzying implications, humanity faces a choice. We can ignore their quiet whispers, dismiss them as mere curiosities, and remain forever bound to our terrestrial cradle, content in our cosmic solitude. Or we can heed their call. We can embrace the mystery, follow the clues, and claim our stellar inheritance. The clouds await. They are the silent sentinels in the southern sky, the beacons in the night illuminating our path forward into the grand and still largely unwritten cosmic saga. What will we choose to do with the light they have offered us? Thank you for joining us on this journey to the edge of understanding. The story of the cosmos is the story of ourselves, written in the language of starlight and gravity. And yet, despite all that, we know there are still mysteries out there, written in the sky, waiting for us to decipher them. What do you think is the greatest secret the Magellanic Clouds are hiding? Is it a story of natural cosmic evolution, or the faint echo of an intelligence that came long before us? Let us know your thoughts in the comments below. If this journey sparked your curiosity, don't forget to subscribe to Astro Horizons and hit the notification bell so you won't miss our next exploration into the great unknown. Until then, keep looking up. Your eyes are lying to you. Everything you think you know about power in the cosmos is wrong. The greatest secrets aren't in the brilliant galaxies, but in the tiny, forgotten ghosts that haunt them. And we've just discovered they are not empty. They are full of monsters. What are they hiding? In the grand tapestry of the cosmos, your eyes are drawn to the spectacle. You see the sprawling, jeweled arms of Andromeda, the churning, star-forming heart of the Triangulum, the incandescent river of light that is our own Milky Way. These are the titans, the galactic empires that command the narrative of the night sky, their brilliance a testament to their power. But this perception, like so many of our senses, is a profound illusion. For in the quiet, shadowy fringes of the universe, where the cosmic glare is dim and our attention seldom wanders, a revolution is unfolding. It is a revolution not of giants, but of ghosts. This story belongs to the dwarf galaxies, those diminutive stellar assemblies so often dismissed as cosmic afterthoughts, the failed experiments of creation. And yet we are now learning they are not failures, but crucibles. Within their humble confines, within these faint and scattered collections of mere millions or billions of stars, the universe forges solutions to its most intractable mysteries. Here, in these unassuming cosmic villages, The true nature of black holes and the ever-present phantom of dark matter are being revealed. For decades, we have been like Plato's cave dwellers, mesmerized by the flickering shadows of giant galaxies projected on the wall of our perception, convinced they were the whole of reality. But we are beginning to turn our heads to look towards the dim light at the mouth of the cave. This is the story of how, on this day, August 1st, 2025, we began to awaken from our grand illusion. The unblinking eyes of our most powerful instruments, from the infrared gaze of the James Webb Space Telescope to the spectroscopic precision of the Dark Energy Spectroscopic Instrument, are pulling back the veil. They are peering into these neglected corners of the cosmos and finding that they are not empty wastelands. They are teeming with a significance that could rewrite the laws of physics. The story of the universe, it turns out, is not just written in the brilliant ink of spiral arms and galactic cores. Its most important secrets, its most profound truths, are whispered in the quiet darkness in the spaces between the giants by the ghosts we are only now learning to see. A new physics is emerging, not with a bang, but with a whisper from the void, challenging everything we thought we knew about the architecture of reality. The titans of the cosmos may hold the power, but it is the dwarfs that hold the key. To understand the universe, you must first understand its architects. Long before the first majestic spiral galaxy unfurled its arms, before the first colossal elliptical galaxy gathered its stellar horde into a glittering ball of fire, there were the dwarfs. They were the first stones laid in the cosmic cathedral, the humble beginnings from which all grandeur would eventually rise. Picture the scene. It is a mere few hundred million years after the Big Bang, a time so ancient it strains the very concept of time. The universe is not the cold, dark expanse we know today. It is a frantic, seething cauldron of almost pure hydrogen and helium, a dark and turbulent place punctuated only by the fierce, brilliant light of the first truly monstrous stars, behemoths, hundreds of times more massive than our sun, destined to live fast and die young in cataclysmic explosions. In this primordial chaos, the quiet, incessant patience of gravity began its work. It is the most patient force in the cosmos, a slow and steady sculptor. It gathered the first wisps of gas, pulling them together. More importantly, it gathered the first pockets of dark matter, the invisible scaffolding upon which the visible universe would be built. Where these pockets of dark matter were densest, they formed gravitational wells, gentle cosmic eddies in the swirling river of creation. Gas fell into these wells, cooled and ignited, giving birth to the first self-contained islands of light, the proto-dwarf galaxies. For billions of years, these were the universe's primary building blocks. The cosmos we see today was constructed through a relentless process of cosmic cannibalism. Through mergers and accretions, these dwarf galaxies collided their stars, and gas ripped apart and reassembled into ever larger structures. Their matter was the mortar and stone used to erect the grand spirals and ellipticals that now dominate the sky. But not all of them were consumed. Many persist, ancient relics orbiting giants like our Milky Way, their low luminosities making them elusive ghosts in the night. Others drift in the profound solitude of the intergalactic void, lonely witnesses to the universe's violent youth. The Magellanic Clouds, our closest and most famous companions, are living fossils of this era. The Large Magellanic Cloud, or LMC, with its 30 billion stars, and the Small Magellanic Cloud, the SMC, with a mere 3 billion float at distances of 160,000 and 200,000 light-years, respectively. They are not merely satellites. They are time capsules, pristine remnants of a younger, wilder cosmos. To look at them, is to look back in time to hear the echoes of our own galaxy's violent birth whispered across the gulf of space. They are the surviving architects holding the original blueprints of creation. There is a fundamental deception at the heart of every dwarf galaxy. When you look at one, you are seeing a lie. The stars, the glowing nebulae, the shimmering veils of interstellar gas, all of it is just froth on the surface of a much deeper, darker ocean. These galaxies are ruled by an invisible tyrant dark matter. In a grand galaxy like our own Milky Way, the balance of power is more equitable. The luminous matter we can see the stuff of stars and planets and people makes a respectable stand against the unseen. But in dwarfs, the ratio is grotesquely, almost comically skewed. Their mass-to-light ratios can exceed 1,000 to 1. Picture what that means. For every single kilogram of matter, you can see there is a ton of matter you cannot. It is as if the entire visible galaxy, with its billions of stars and beautiful structures, is merely a dusting of frost on a colossal, invisible mountain. This discovery, pieced together over decades by the meticulous and often ignored work of astronomers like Vera Rubin and Fritz Zwicky, was a profound shock to the scientific establishment. Rubin, observing the rotation of spiral galaxies, found that the outer stars were moving far too fast. There wasn't enough visible matter to hold them in their orbits. They should have been flung off into intergalactic space. The only explanation was a vast, unseen halo of mass. Zwicky, studying the Coma cluster of galaxies, came to the same conclusion. Something unseen was binding the universe together. Their conclusions were met with skepticism, but the evidence was undeniable. This meant these tiny galaxies were not tiny at all. They were behemoths cloaked in darkness, their vast halos of invisible matter extending far beyond their luminous shores, their gravitational influence disproportionate to their faint glow. This overwhelming dominance makes them the perfect laboratories for studying this elusive substance. Here in these quiet cosmic backwaters, the phantom of dark matter is not a subtle influence, a minor correction to our equations. It is the undisputed king. It is the architect that laid down the gravitational blueprint for the galaxy's formation. It is the shepherd that guides the orbits of its stars. And it is the tyrant whose gravitational dictates shape every aspect of the galaxy's existence. To understand dark matter, we must look not to the bright centers of galactic empires, but to these dim, forgotten kingdoms where the invisible reigns supreme. For decades, the story of black holes was a tale of two extremes, a cosmic bestiary populated only by mice and elephants. On one end, you had the stellar mass black holes, the compact corpses of massive stars weighing a few dozen times the mass of our sun. These are the common predators of the galactic plains. On the other, you had the supermassive black holes, or SMBHs, the gravitational titans lurking in the cores of giant galaxies, weighing millions or even billions of solar masses. These are the leviathans, the elder gods of the cosmic ocean. But between these two realms lay a vast, unnerving desert. Where were the middle-class black holes? Where were the intermediate mass black holes, or IMBHs, the missing links weighing hundreds to thousands of solar masses? For years they were ghosts in the cosmological machine, their existence a theoretical necessity, but an observational phantom. Models of galaxy formation demanded their presence. How else could you grow a supermassive black hole? It seemed impossible to leap from a 30 solar mass seed born from a single star to a billion solar mass monster without intermediate steps. That is not evolution, it is magic. There had to be a bridge, a pathway for growth. Yet the universe remained stubbornly silent. The conventional wisdom held that such objects, if they existed, must be exceedingly rare, perhaps forged in the chaotic, hyper-dense hearts of ancient globular clusters, where stars and stellar remnants could collide and merge in a gravitational mosh pit. The idea that they might thrive in the placid, low-density environments of dwarf galaxies seemed unlikely. These quiet systems, it was thought, simply lacked the gravitational muscle and the raw material to build such beasts. The search was long frustrating and littered with the corpses of false positives. Astronomers would spot a tantalizing flicker of X-rays or a star moving at an odd velocity, only to find a more mundane explanation upon closer inspection. The desert remained barren. It was a profound and unsettling gap in our understanding, a missing chapter in the biography of the universe. Were we fundamentally wrong about how galaxies grow, or were we simply not looking in the right place? The hunt for the IMBH became one of the great quests of modern astrophysics, a search for a ghost that many were beginning to believe was just a figment of our theoretical imagination. They were chasing a chimera, a monster that existed only in the pristine mathematics of their models, but not in the messy reality of the cosmos. High atop Kitt Peak in Arizona, under skies so dark they seemed to press down on the Earth, a new eye opened to the cosmos. It was not a lens of polished glass, but a marvel of engineering, the Dark Energy Spectroscopic Instrument, or DESI, mounted on the historic Nicholas U. Mayle 4-meter telescope. Its purpose was to conduct the largest, most detailed three-dimensional survey of the universe ever attempted to map the unseen architecture of dark energy. But its gaze captured something far more profound and far more monstrous than its name suggested. In February of 2025, the first major data release sent a shockwave through the astronomical community. DESI had not just glimpsed the ghosts in the machine, it had found a city of them. By meticulously analyzing the light from over 500,000 galaxies, DESI's precision spectrographs pierced the veil of starlight that had hidden the hearts of dwarf galaxies for so long. The instrument's power lay in its robotic array of 5,000 swiveling fiber optic positioners, a swarm of mechanical fireflies that could, in a matter of minutes, pivot to capture the light from thousands of individual galaxies at once. It was searching for active galactic nuclei, or AGN, the blazing signatures of matter being consumed by a black hole. In massive galaxies, AGN are brilliant torches, outshining all the stars of their host combined. But in dwarfs, they are flickering candles often lost in the overwhelming glare of intense star formation. Yet DESI's robotic eyes could dissect the light with unprecedented clarity, hunting for the specific emission lines, the unique chemical fingerprints of superheated gas spiraling into an abyss. The result was an astonishing haul, a census of monsters that defied all expectation. The data revealed 300 new, confirmed intermediate mass black holes and an incredible 2,500 active black holes of varying sizes, all lurking where they were least expected, inside the unassuming faint glow of dwarf galaxies. The long, frustrating search was over. The desert was not empty. It was an oasis teeming with life. The chimera was real. And suddenly the story of the cosmos, the tale of how its grandest structures and most powerful objects came to be, had to be completely rewritten. The ghosts were no longer ghosts. They were kings. The DESI data was not a discovery. It was a revelation. A paradigm had not just shifted, it had shattered. The sheer numbers were staggering, forcing a complete and painful re-evaluation of cosmic ecology. Why were there so many of these monsters in such unassuming homes? A study from the University of Utah, published in March of 2025, described the finding as a vast discovery, one that fundamentally challenged every existing model of black hole formation. It was as if biologists, having only ever seen mice and elephants, suddenly discovered that every small town in the world was secretly home to a pride of lions. The comfortable, ordered ecosystem of the cosmos had been thrown into chaos. The sheer density of intermediate mass black holes in these dwarf systems implied something profound. Their formation was not a rare fluke event, a lucky accident in a crowded globular cluster. It was a common, perhaps even necessary part of dwarf galaxy evolution. The ghosts were not aberrations. They were part of the original blueprint. They were not an afterthought. They were a feature. This flood of new data posed a deep and fundamental question about how the universe builds its most extreme objects. Was it a bottom-up process, a slow and patient construction project where stellar mass black holes merge over billions of years, gradually building up to intermediate and then supermassive scales? Or was it a top-down approach, a process of violent and rapid creation where enormous clouds of primordial gas could collapse catastrophically, birthing massive black hole seeds from the very beginning? The two paths represent vastly different visions for the early universe. One is a story of slow, steady, incremental growth. The other is a tale of primordial giants born fully formed in the crucible of the cosmic dawn. For decades, the debate had raged, limited by a frustrating lack of evidence. But now, with this flood of monsters from the DC survey, we finally had a population to study. The answer to this profound cosmological question, it seemed, was hidden within the unique chemistry of these ancient, forgotten stellar cities. So what makes a dwarf galaxy the perfect nursery for a fledgling monster? The answer lies not in what they have, but in what they lack. It lies in the composition of the universe's first ingredients. The very early cosmos was almost entirely composed of hydrogen and helium, the two lightest elements forged in the fires of the Big Bang. Heavier elements, everything from the carbon in your body to the iron in your blood, which astronomers in a charmingly blunt shorthand call metals, were forged later in the thermonuclear hearts of stars and scattered through the cosmos in the violent death throes of supernovae. Dwarf galaxies, being ancient and relatively placid systems, have largely retained this pristine, metal-poor chemistry. They are chemically primitive, a direct link to the universe's babyhood. This turns out to be the crucial factor. In a modern metal-rich gas cloud, like the Orion Nebula in our own Milky Way, these heavy elements act as incredibly efficient coolants. They radiate heat away, allowing the cloud to lose energy, and as it cools, it fragments into thousands of smaller, denser clumps, each one destined to become a star. It's a beautifully productive process. But in a metal-poor cloud, like those found in the early universe and preserved in today's dwarf galaxies, this vital cooling mechanism is absent. The gas remains hot, its internal pressure fighting against the pull of gravity. It stubbornly resists fragmentation. This allows for a truly monolithic collapse. Instead of forming a sparkling cluster of thousands of stars, the entire colossal cloud containing the mass of tens of thousands of suns can implode under its own gravity, collapsing directly into a single massive object, a direct collapse black hole. This is the top-down model in its most dramatic form. It bypasses the slow, messy business of star formation and stellar evolution entirely. It is a cosmic shortcut, a direct route to creating a massive black hole seed. The quiet, chemically primitive nature of dwarf galaxies, once seen as a sign of their insignificance, was in fact their defining strength. They were the universe's preferred nurseries for the seeds of giants, the quiet cradles where the first true monsters were born. For years, it was a subtle anomaly, a gravitational whisper in our own backyard. Stars on the outskirts of the Large Magellanic Cloud were moving too fast. Some were being flung outwards with such incredible velocity that they were destined to escape the LMC entirely and become rogue travelers hurtling through the dark halo of the Milky Way. Something was acting as a colossal slingshot at the LMC's core, a gravitational engine of immense power. But what could it be in 2025, after years of painstaking observations piecing together stellar motions from projects like the Gaia Space Observatory? Astronomers finally confirmed the culprit, a hidden monster, an intermediate mass black hole candidate weighing around 100,000 solar masses. It was a beast that, according to the prevailing wisdom, had no right to be there. The LMC, for all its charm and its 30 billion stars, was considered too small, too diffuse, too lacking in a dense central bulge to host such a significant black hole. And yet there it was, its presence betrayed by the hypervelocity stars it ejected like cosmic buckshot. This discovery defied all expectations. It was a stunning vindication for those who believed that IMBHs were not just theoretical curiosities, but it was also a profound challenge. If our closest, most well-studied dwarf companion could hide such a secret, what else was lurking in the depths of these faint, unassuming galaxies? The discovery demonstrated that even our most familiar celestial neighbors harbored secrets of immense scale. The LMC was not just a satellite galaxy, a passive companion to the Milky Way. It was a system with a powerful central engine, a gravitational heart of its own, capable of shaping its own destiny and flinging messengers of its violent nature directly into our path. It was a stark and humbling reminder that even the things we think we know best can hide the most profound surprises. The cosmos is not obligated to conform to our expectations, and our own galactic backyard, it turns out, is a much wilder and more interesting place than we had ever imagined. One of the great nagging mysteries of cosmology has always been speed. How did the universe form supermassive black holes so quickly? Observations of distant quasars, unimaginably bright beacons powered by accreting SMBHs, showed that monsters weighing billions of solar masses already existed when the universe was just 700 million years old, a mere blink of an eye in cosmic terms. Growing a black hole that big, that fast, seemed impossible. It was like expecting a newborn baby to grow to the size of a blue whale in its first year. The conventional bottom-up models, where stellar mass black holes slowly merge and grow over eons, simply couldn't work fast enough. The timeline was too short. The math didn't add up. There had to be another way. Then, in July of 2025, the James Webb Space Telescope delivered the missing piece of the puzzle. Peering deeper into cosmic dawn than any instrument in history, its golden mirrors collecting photons that had traveled for over 13 billion years, JWST captured an image of a tiny, distant dwarf galaxy. It was a faint red smudge, a mere embryonic island of light in the vast darkness. But at its heart was something impossibly large, something that defied all logic, an oversized black hole already immense despite its host's tender youth. The mass of the black hole was a significant fraction of the mass of the entire galaxy, a ratio unheard of in the modern universe. The data was consistent with only one explanation: a direct collapse black hole. Here was the smoking gun. JWST had not just seen an ancient galaxy, it had witnessed the aftermath of a primordial creation event. A pristine metal-free gas cloud had imploded under its own gravity, bypassing the star formation phase entirely to create a hefty black hole seed in one swift, cataclysmic event. This was the shortcut the universe needed. By seeding the first dwarf galaxies with these heavyweight champions, from the very beginning the cosmos had a clear and rapid pathway to building the behemoths that would become the quasars, the brilliant lighthouses that would illuminate the early darkness and preside over the formation of the first great galaxies. The mystery of speed had been solved not with a slow crawl, but with a giant leap. For too long, we imagined black holes as passive entities, cosmic sinkholes that did nothing but consume. We now know this picture is fundamentally wrong. A black hole is not a passive drain. It is an active engine, a galactic sculptor that profoundly shapes the destiny of its host galaxy. As a black hole accretes matter, it doesn't just swallow it silently. The infalling gas and dust and shredded stars don't fall straight in. They are caught in a gravitational whirlpool, forming a swirling incandescent accretion disk. Here the material is superheated to millions of degrees, crushed and twisted by immense gravitational and magnetic forces, erupting into powerful outflows, colossal bipolar jets of gas and radiation that blast outwards at nearly the speed of light. In a giant galaxy, these jets are spectacular sometimes, stretching for millions of light years, far beyond the visible boundary of the galaxy itself. But in the compact, crowded environment of a dwarf galaxy, their impact is even more dramatic. These outflows act as a powerful regulator, a form of galactic self-control. They plow through the galaxy's precious reserves of star-forming gas like a cosmic snowplow. In some regions, they compress the gas, triggering furious, short-lived bursts of new star formation. But simultaneously, they can blast other regions completely clear of gas-quenching star birth entirely, and starving the galaxy of its future potential. This delicate feedback loop, this intricate dance between consumption and creation, dictates the galaxy's entire evolution. It determines how many stars the galaxy can form, what shape it will take, and whether it will grow or fade away. The black hole is not just a resident of the dwarf galaxy, it is its beating heart and its fiery breath. It is the central architect, the cosmic artist that sculpts the galaxy's form and ultimately decides its fate. The relationship is not one of a parasite and its host, but a deep, violent, and creative symbiosis that lies at the very heart of cosmic evolution. The standard model of cosmology, known as lambda CDM, has been the reigning king of physics for decades. It is an elegant and powerful framework, a theory that has successfully explained a vast range of cosmic observations, from the afterglow of the Big Bang to the large-scale structure of the universe. Its core tenet is that the cosmos is governed by two mysterious and dominant components: the gravitational influence of cold dark matter, the CDM part, and the accelerating expansion driven by a force we call dark energy, the lambda. For years, this model has been our most trusted guide to the universe. But all kings must eventually face a challenger. In June of 2025, a paper from a team of researchers at the University of Texas at San Antonio, Utah, proposed a radical and heretical idea. What if, in certain cases, specifically in dwarf galaxies, we didn't need dark matter to explain their dynamics? What if the black hole itself was enough? The study suggested that the immense gravity of a centrally located supermassive black hole, or even a large intermediate mass one, could under the right conditions mimic the gravitational effects typically attributed to a vast halo of dark matter. It could explain the rapid rotation of the galaxy's outer stars without invoking an invisible substance. This was not just a minor tweak to the theory, it was a direct challenge to the crown. It was cosmology's equivalent of suggesting that perhaps the sun does not revolve around the Earth. The idea was met with immediate and intense debate. It raised the tantalizing possibility that dark matter might not be the ubiquitous, all-powerful substance we imagined, but perhaps a more complex phenomenon, or in some cases, not necessary at all. Could some of the effects we attribute to dark matter actually be the work of gravity in its most extreme form? The black hole, once a mere curiosity, a bizarre consequence of Einstein's equations, was now being proposed as a potential usurper to the throne of lambda CDM. The battle for the soul of cosmology had begun. We now enter the realm of speculation, where the firm ground of observation gives way to the thrilling vertigo of possibility. If advanced civilizations exist, where might they live? Perhaps not on tranquil planets orbiting stable sun-like stars, but in the most extreme and energy-rich environments imaginable, the churning warped spacetime around a spinning black hole. Sir Roger Penrose, a mind that saw the universe in its deepest and most elegant geometric forms, conceived of a mechanism for extracting energy from such an object. Surrounding a spinning black hole is a region called the ergosphere, where spacetime itself is dragged along with the black hole's rotation, a cosmic whirlpool from which nothing can stand still. The Penrose process theorizes that a sufficiently advanced civilization could throw an object, a container of waste, perhaps into the ergosphere, on a precise trajectory. They could then split the object in two, arranging it so that one half falls into the black hole while the other half is ejected, emerging with more energy than the original object had. The black hole's rotational energy is converted into mass, a near-limitless font of power. Could we detect such a colossal engineering project, any technological process, no matter how advanced, must obey the unforgiving laws of thermodynamics. It must produce waste heat. It is an unavoidable signature of civilization. A reanalysis of archival data from the now-retired Spitzer Space Telescope in 2025 revealed a tantalizing clue. Several distant dwarf galaxies, too faint to be of much interest, before showed anomalous infrared excesses, a faint, inexplicable glow of heat that could not be explained by star formation or dust. It was a thermal signature consistent with the waste heat from a civilization-scale energy harvesting operation. The implications are profound. We may not be able to hear their whispers or see their cities, but we might just be seeing the faint warmth of their forges burning bright in the lonely darkness of a distant dwarf galaxy. We could be witnessing the technosignatures of a Kardashev Type 2 civilization, a society that has mastered the energy output of its local star, or in this case, its local black hole. The whispers from the ergosphere are not of sound, but of thermodynamics, a language of energy and entropy that may be the most universal signal of all. A black hole, we are told, is a place where information is lost forever. According to the classical physics of Einstein's general relativity, anything that crosses the event horizon, the point of no return, is severed from the rest of the universe, its story erased, its every detail crushed to an infinitesimal point of infinite density. It is the ultimate censorship. But in the 1970s, a young physicist named Stephen Hawking, in a breathtaking feat of intellectual synthesis, blended the rigid laws of gravity with the bizarre probabilistic rules of quantum mechanics. He showed that black holes are not perfectly black. They have a temperature, and they emit a faint ethereal glow of particles, now known as Hawking radiation. Over incomprehensible timescales, they slowly evaporate and disappear. This led to one of the deepest and most persistent conflicts in modern physics, the information paradox. If the black hole evaporates completely, what happens to the information of everything that fell inside quantum mechanics has a sacred law: information can never be truly destroyed. So where does it go? One of the most profound and poetic ideas to emerge from this paradox is the holographic principle. Championed by physicists like Gerard 't Hooft and Leonard Susskind, it proposes the radical notion that all the information about the three-dimensional interior of the black hole is somehow encoded on its two-dimensional surface, the event horizon, like a cosmic hologram. If this is true, then the outgoing Hawking radiation is not random thermal static. It is the story of the black hole's life, the information of every star and dust cloud it ever consumed slowly being broadcast back into the universe, scrambled but not erased. Could an advanced intelligence take this a step further? Could they use a black hole as the ultimate information repository, a cosmic archive where the history, science, and art of an entire civilization are encoded into its quantum structure? Could they write their story onto the fabric of space-time itself to be read eons later by anyone with a sensitive enough radio telescope and an understanding of quantum gravity? The faint microwave static from these distant dwarf galaxies might not be noise. It could be the ghosts of forgotten libraries waiting for a translator. The Small Magellanic Cloud has always been a bit of an oddball. Its shape is irregular, a messy, sprawling collection of stars and gas. Its star formation is chaotic and bursty, a stark contrast to the more majestic, almost stately evolution of its larger companion, the LMC. For years, astronomers chalked this up to the gravitational bullying of the Milky Way, our own galaxy's tides distorting its smaller neighbor. But in 2025, a detailed kinematic study tracking the precise motions of thousands of its stars confirmed a far more dramatic and intimate reason for its strangeness. The SMC is not a single entity. It is two distinct dwarf galaxies, seen one in front of the other from our earthly perspective, caught in the midst of a slow-motion collision and a multi-billion-year gravitational tug-of-war. This discovery of a sundered cloud, a galaxy torn in two, immediately deepened the mystery. If the SMC was two separate systems, did it host two separate black hole populations? The question was electric. X-ray flares detected by the Chandra Observatory suggested a dormant IMBH stirring in the foreground component, its long slumber occasionally disturbed by a passing gas cloud or an unlucky star. The background component, however, remained stubbornly silent, its heart a complete unknown. This duality offered a perfect natural experiment. Did the two black holes co-evolve? Are they destined to one day merge, unleashing a colossal burst of gravitational waves that will ripple across the cosmos? Could their gravitational dance be responsible for the SMC's peculiar structure and its violent bursts of star formation? And what of the strange repeating fast radio bursts, the FRBs, that seemed to emanate from the SMC's direction? These millisecond-long blasts of intense radio energy are one of the greatest puzzles in modern astronomy. Perhaps they were not natural phenomena at all. Perhaps they were the rhythmic pulse of a navigational beacon or a desperate distress call, a signal from some ancient outpost caught in the cosmic crossfire of a billion-year galactic merger. The SMC was no longer just a quaint satellite galaxy. It was a scene of cosmic violence, a laboratory for galactic mergers, and potentially the home of a mystery that was not just astronomical, but technological. Most of the time, a black hole is a creature of stealth. Unless it is actively feeding on a steady diet of interstellar gas, it is completely invisible. A perfect patch of black against the blackness of space, detectable only by its subtle gravitational influence on the objects around it. But sometimes a star wanders too close. And when it does, the universe puts on one of its most astonishingly violent spectacles. In a 2025 analysis of archival data from the Chandra X-ray Observatory, astronomers witnessed just such an event in a distant anonymous dwarf galaxy. A star drawn in by the irresistible gravity of the galaxy's central IMBH was caught in a fatal embrace. The immense tidal forces of the black hole, the brutal difference in gravity between the near and far side of the star, stretched and squeezed it like putty. It was torn apart in a process with a grimly descriptive name: spaghettification. This is a tidal disruption event, or TDE. As the stellar material, now a long, thin stream of superheated plasma, was pulled into a swirling accretion disk, Around the black hole, it heated up to millions of degrees, unleashing a brilliant, short-lived flare of X-rays that illuminated the darkness. For a few brief months, the invisible became spectacularly visible. These events are particularly powerful probes in dwarf galaxies. In a massive galaxy like the Milky Way, the galactic core is a crowded, messy place, and the faint flare of a TDE can be lost in the glare. But in the relatively clean, low-background environment of a dwarf galaxy, the flare from a TDE stands out like a beacon in the night. Each flash is a momentary revelation, a brief but brilliant glimpse into the hidden population of black holes that would otherwise remain unknown. It is a visceral reminder of their dual role as both builders and destroyers of their cosmic domains, silent predators that for a moment are caught in the act of their violent creative work. Where did the first black holes come from? The direct collapse model provides one compelling answer, but another even more exotic possibility lurks in the very first moments of creation. In the instant after the Big Bang, the universe was an unimaginably dense and turbulent soup of energy and quantum fields. It is theorized that in this chaotic environment, tiny random quantum-scale fluctuations in density could have become amplified by the universe's explosive expansion, creating regions so dense that they collapsed directly into black holes without ever having been stars or even gas clouds. These are the primordial black holes, or PBHs. They are ghosts from the dawn of time itself. They could range in size from the mass of an asteroid to thousands of times the mass of the Sun. For decades, they have been a leading, if controversial, candidate for the identity of dark matter. If this hypothesis is true, it would be a discovery of breathtaking elegance. The dark matter halos surrounding dwarf galaxies would not be made of some exotic, undiscovered new particle, but would be vast, ancient swarms of these primordial ghosts. This would neatly solve two of the biggest problems in cosmology at once. The PBHs would be the dark matter, and over time, within the dense confines of a dwarf galaxy's halo, they could slowly sink to the center merge and accrete gas, growing to become the intermediate mass black hole seeds we now see in the hearts of these galaxies. Dwarf galaxies with their extreme dark matter content become the prime hunting ground for these ancient relics. Finding definitive proof perhaps by detecting the final bright gamma-ray flashes from a small PBH evaporating via Hawking radiation, as a 2025 analysis of Fermi lat data proposed, would be one of the greatest discoveries in the history of science. It would confirm the origin of both black holes and dark matter in a single elegant stroke, revealing that the universe's greatest mysteries were born together in the same primordial fire. In science, the object that doesn't fit the pattern is often the most important one. It is the anomaly, the outlier, the wrench in the gears of a beautiful theory that forces us to confront our own ignorance and seek a deeper truth. For years, the rule seemed simple and unbreakable. Dwarf galaxies are dominated by dark matter. Then came AGC 11495, a meticulous study published in April 2025 based on 40 hours of observation with the Very Large Array Radio Telescope confirmed the unimaginable. Here was a dwarf galaxy with practically no dark matter at all. Its rotation, the speed of its stars and gas, could be explained entirely by the mass of its visible components. It was a galaxy with no shadow, an anomaly that struck at the very heart of galaxy formation models. How could such an object exist? Did it somehow lose its dark matter halo in a violent past collision with a larger neighbor, an act of galactic bullying that stripped it bare? Or was it born this way, a naked galaxy formed from a pocket of the universe, somehow deficient in the dark matter scaffolding that underpins everything else? The very existence of AGC 114905 lent new explosive credence to the heretical idea that black holes could in some cases substitute for dark matter. Perhaps this galaxy was not missing its shadow, but had simply replaced it. Maybe a large, centrally located black hole, or perhaps a swarm of smaller ones, provides all the gravitational glue this particular system needs, rendering a dark matter halo obsolete. AGC 114905 is a paradox made manifest in stars and gas. It is a cosmic koan, a riddle that challenges our most fundamental assumptions. It forces us to confront the uncomfortable possibility that our neat and tidy rules are not rules at all, but merely suggestions, and that the universe is far more creative and far stranger in its methods of construction than we have ever dared to imagine. In March of 2025, the European Space Agency's Euclid telescope, a mission designed with surgical precision to map the geometry of the dark universe, released its first major catalog of observations. While its primary targets were the subtle distortions in spacetime caused by dark matter and dark energy, its wide, sensitive gaze captured a breathtaking bonus to 674 new, previously unknown dwarf galaxies. It was like a biologist searching for rare orchids in a vast jungle, stumbling upon thousands of entirely new species of animal life. The cosmic ecosystem was far richer and more diverse than we had realized. The haul revealed a stunning diversity of forms. There were the faint, diffuse smudges of ultra-faint dwarfs, little more than ghostly collections of a few thousand stars barely held together by gravity. And then there were the blue, compact dwarfs, blazing with the brilliant, violent light of furious star formation, their structures often marked by rippling rings and delicate shells of stars, the telltale scars of recent galactic mergers. These merger remnants were particularly tantalizing. When two dwarf galaxies collide, their central black holes, once the undisputed kings of their own small realms, are destined to sink to the core of the newly formed larger galaxy. There they begin a long, slow gravitational death spiral, orbiting each other for millions of years, before they finally merge, unleashing a colossal burst of gravitational waves that will shake the very fabric of spacetime. The beautiful chaotic structures seen by Euclid were snapshots of this process in action. They were visual proof of the hierarchical growth model where black holes and their host galaxies evolve together through a long and violent history of collisions and cannibalism. Each of Euclid's 1,000 new worlds was a new piece of the puzzle, a fresh clue in the epic story of cosmic assembly, a testament to the dynamic, ever-changing nature of the cosmos. For years, a quiet war has been waged in the heart of cosmology, a subtle but persistent conflict known as the core-cusp problem. The standard model of cold, dark matter, for all its successes, makes a very specific prediction. The dark matter halos of galaxies, especially dwarf galaxies, should be cuspy. That is, the density of dark matter should rise sharply and steeply to a fine point in the galactic center. But when astronomers looked meticulously mapping the gravitational fields of nearby dwarfs, they found something different. Many of them had cores regions, where the dark matter density flattened out near the center, refusing to form the predicted cusp. It was a glaring and uncomfortable contradiction. What was erasing the cusp? The discrepancy launched 1,000 theoretical ships. One popular theory proposed a new kind of dark matter, one that was not perfectly cold, but could interact with itself, its particles bouncing off each other and smoothing out the central density. But a more elegant and perhaps more violent solution was emerging from the world of supercomputer simulations. A 2025 paper in the monthly notices of the Royal Astronomical Society, analyzing the state-of-the-art fire cosmological simulations, showed a convincing culprit, the black hole. The simulations, which modeled the formation of galaxies with breathtaking fidelity, demonstrated how the powerful outflows and jets from a central IMBH could act like a cosmic snowplow. Over millions of years, these repeated outbursts would violently scour dark matter particles out of the galactic core, pushing them into wider, less dense orbits, and transforming the predicted pristine cusp into the observed messy core. It was a beautiful synergy of theory and observation, suggesting that the visible universe and the dark universe were not just coexisting peacefully. They were locked in a dynamic physical struggle, with the black hole acting as the powerful mediator, shaping the very fabric of the invisible world around it. The heart of the galaxy was not a quiet place, but a battlefield, and the black hole was its most ferocious warrior. Let us take one final step into the speculative darkness. If dark matter is indeed made of particles that can annihilate each other when they collide, converting their mass directly into energy, what would happen in the hyper-dense core of a dwarf galaxy's halo where these particles are packed most tightly? A 2025 white paper from a team at Caltech explored this question, reviving a fascinating and haunting hypothesis: the dark star, or in this case, the dark dwarf. In this scenario, the ferocious energy released from dark matter annihilation could become the primary power source for a celestial object. Imagine a vast cloud of primordial gas beginning to collapse under its own gravity. Normally, this collapse would continue until the core became hot and dense enough to ignite nuclear fusion, giving birth to a star. But in a dense, dark matter environment, the annihilation process could kick in, first releasing a flood of energy that pushes back against gravity, halting the collapse. The result would be a new kind of star one, not powered by the fusion of atoms in its core, but by the slow, steady burn of dark matter in its halo. Such a star could glow eternally for billions or even trillions of years long after its conventional cousins have faded to black. Now take this idea further. Could an entire dwarf galaxy become such an entity, a dark dwarf galaxy, powered not by the finite light of its stars, but by the silent, relentless annihilation at its core, could sustain itself across the eons, a self-perpetuating island of stability? And if such a thing existed, what would it mean for life? An advanced civilization arising within such a system would have access to a virtually limitless power source. They could build eternal cities, power automated networks that span geological time, and watch the rest of the universe grow old and die from the safety of their eternally glowing home. It is a staggering thought that in the darkest corners of the cosmos, there might be islands of perpetual light powered by the very substance of the darkness itself. In the constellation of Draco the Dragon lies a dwarf galaxy of the same name. It is one of the Milky Way's faintest and most ancient satellites, a ghostly relic from the dawn of time, barely visible even to our most powerful telescopes. Its name evokes mythology, a celestial beast coiled in the eternal darkness of the northern sky. In July of 2024, the Hubble Space Telescope completed a long and patient study, meticulously tracing the subtle, almost imperceptible movements of Draco's individual stars to map the contours of its internal gravity. When this precious data was reanalyzed with new, more sophisticated models in 2025, it revealed something strange. The distribution of dark matter within the Draco dwarf was not smooth. It was clumpy and uneven, with unexpected concentrations and voids that defied simple explanation. The invisible halo was not a serene, uniform shroud. It was a turbulent, lumpy sea. What could be causing this? Was this the fossilized evidence of past mergers, the undigested and ghostly remains of even smaller galaxies that Draco itself had consumed in its youth? Or was it the signature of something else, something active and alive within its core? Could the gravitational influence of a central, unseen, intermediate mass black hole be stirring the dark matter, creating eddies and currents in the invisible halo, much like a stone dropped in a still dark pond, the Draco Dwarf? This ancient mythological dragon guards its secrets well. Its lair is a place where the visible and the invisible dance in strange and complex ways, hinting that the relationship between stars, black holes, and dark matter is a story far more intricate and mysterious than a simple tale of gravitational attraction. It is a story of interaction, of feedback, of a deep and ongoing physical conversation between light and darkness. For millennia long before telescopes and spectrographs, humans in the southern hemisphere looked up and saw two faint milky patches in the sky detached from the main river of the Milky Way. They were woven into the very fabric of culture, into the oldest stories of our species. To some Polynesian navigators, the masters of celestial wayfinding, they were the celestial canoes, vessels for the spirits of the ancestors, sailing across the cosmic ocean. In 2025, a paper in the Journal of Archaeological Science revealed a stunning connection between these ancient myths and the hard data of modern science. Megalithic sites across the southern hemisphere from Australia to South America, some dating back over 10,000 years, showed precise astronomical alignments. But they pointed not just to the rising and setting of the sun and moon, but to the specific positions of the Large and Small Magellanic Clouds at that time. Why would ancient peoples go to such extraordinary lengths to track these faint, unassuming clouds? Perhaps they were not always so faint. Perhaps in the distant past, our ancestors witnessed something spectacular, a hyper-luminous supernova exploding within the clouds, a brilliant guest star that would have dominated the night sky for months. Or maybe they saw a luminous meteor shower originating from the Magellanic Stream, the long river of gas connecting the clouds to our own galaxy, a celestial fireworks display that would have seemed like a sign from the gods. Or perhaps, and here we return to speculation, they saw something else entirely. Could the temporary brightening of a dark dwarf galaxy, or the glowing exhaust from an interstellar stellar engine, have been interpreted as a divine sign, a godly canoe crossing the heavens? The myths may not be just stories. They may be the oldest surviving records of astronomical observation, a cultural echo of cosmic events that connects our most ancient ancestors to the deepest and most profound mysteries we are grappling with today. The sky, it seems, has always been speaking to us. We are only now beginning to relearn its language. The Event Horizon Telescope, a global network of radio dishes synchronized to function as a single Earth-sized observatory, had already achieved the impossible. It had imaged the shadows of two supermassive black holes, M87 Phaethor and Sagittarius A, giving humanity its first glimpse into the abyss. By July of 2025, after years of painstaking observation and the Herculean task of processing petabytes of data, it set its sights on a new, more challenging target, the 100,000 solar mass IMBH candidate at the heart of the Large Magellanic Cloud. The image it produced was faint, the resolution pushed to its absolute physical limit, a blurry ring of light against the darkness. But it revealed a stunning anomaly. The relativistic jets blasting from the black hole's poles were asymmetric, and their radio emissions carried a subtle modulated pattern, a faint rhythmic pulse, layered on top of the chaotic noise of the accretion disk. It looked suspiciously impossibly like a signal. Simultaneously, a separate team, using highly sensitive microwave detectors to analyze the background hum of Hawking radiation from the same object, reported strange fluctuations. There were subtle deviations from the predicted thermal randomness patterns that bore an uncanny and chilling resemblance to quantum error-correcting codes the very techniques humans use to protect information in our own fledgling quantum computers. The implications were both chilling and exhilarating. Was this the evidence of a cosmic archive? Was an ancient intelligence using the fundamental physics of the black hole itself, the structure of its jets, the quantum state of its evaporation, to encode a message, a vast library of knowledge waiting for a civilization with the technology to read it? The heart of the Large Magellanic Cloud was not just a gravitational engine. It could be a broadcasting station transmitting the story of a lost civilization into the cosmos, a message in a bottle thrown into the river of time. As these discoveries mounted throughout 2025, from the flood of black holes found by Dyson to the tantalizing hints of technology in the LMC, they began to converge on a profound and deeply unsettling ethical dilemma. If dwarf galaxies, and particularly our own Magellanic Clouds, are not just natural relics, but are potentially hosts to dormant alien technology, ancient archives, or even entire ecosystems powered by exotic physics, what is our responsibility? The question echoed in the halls of academia and government. A fiery debate erupted at a 2025 SETI Institute symposium. One faction, the preservationists, argued for caution. They proposed that these systems should be declared a form of cosmic heritage, akin to a UNESCO World Heritage Site, to be studied non-invasively but left untouched. To activate dormant technology without understanding its purpose, they argued, could be catastrophic. It could be like a child playing with a loaded gun, potentially awakening hostile systems, or destabilizing the delicate galactic environment in ways we cannot possibly foresee. The other faction, the interventionists, argued for engagement. Humanity, they countered, faces a battery of existential threats: climate change, resource depletion, self-destruction, that the secrets hidden within these dwarfs could solve. Limitless energy from the Penrose process blueprints for interstellar travel from a cosmic archive. These were not just scientific curiosities, they were potential lifelines. To leave such a resource untapped out of an abundance of caution, they argued, would be a betrayal of our own species' future. This debate is not academic. It is underscored by a terrifyingly real ticking clock. We know that in roughly 2 billion years, the Magellanic Clouds are destined to be fully assimilated by the Milky Way, their unique structures and whatever secrets they hold erased forever in a final fiery merger. We stand at a cosmic crossroads, forced to ask one of the most difficult questions in our history. Do we learn their lessons before they are lost forever, or do we risk destroying ourselves with the very wisdom we seek? The choice between preservation and progress has never been starker, and the fate of our civilization may hang in the balance. The year 2025 was a watershed, a moment when our perception of the universe was fundamentally and irrevocably altered. But it was only the beginning. The revelations from Dyson, JWST, and Chandra have paved the way for a new generation of explorers, both human and robotic. The Nancy Grace Roman Space Telescope, set to launch in 2027, will conduct a deep survey of tens of thousands of dwarf galaxies, hunting for the faint flicker of AGN and mapping their dark matter halos with its unprecedentedly wide infrared gaze. The Square Kilometer Array, the SKA, an immense radio telescope sprawling across 2 continents, will listen with unparalleled sensitivity to the radio whispers from the Small Magellanic Cloud, searching for artificial patterns in the cosmic static. And the proposed Magellanic mission, a fleet of small nimble CubeSats, could one day fly directly through the Magellanic Stream, sampling its gas for the isotopic technosignatures of ancient propulsion systems, or the waste products of forgotten industry. We began this story believing dwarf galaxies were afterthoughts, the failed footnotes of cosmic history. We now understand they may be the crucibles of creation, the nurseries of monsters, and perhaps the libraries of the gods. They teach us that the universe is not just grander than we imagine, it is grander than we can imagine. And as we stand on this next horizon, gazing out at these faint, ghostly lights, we are reminded of the true purpose of our relentless quest for knowledge. It is not just about finding answers. It is about learning to ask better, more profound questions. And in doing so, finally understanding our own small but significant part in this magnificent, bewildering, and unending cosmic story. The greatest secrets are still out there, waiting in the darkness. The journey has just begun. Thank you for joining us on this journey to the edge of understanding. If these ideas have sparked your curiosity, don't forget to subscribe to Astro Horizons and hit the notification bell so you won't miss our next exploration into the cosmos. What do you think is the greatest secret dwarf galaxies are hiding? Let us know in the comments below. As always, keep looking up and keep wondering.